In this third video from Module 19, we consider glacial erosion and deposition. Well, we'll start off with some factors in glacial erosion. First thing we can say, and I like to say this a lot when I talk about glaciers, glaciers don't create landscapes. They alter existing ones. So when you look at a peak like this, these minarets, imagine this as a rounded mountain at one time that was modified by glaciers, where glaciers came along later and removed a lot of material and really sharpened the peak and made it more dramatic looking. The second thing to point out is the effectiveness of a glacier is dependent on its volume, how much material is being carried, and its velocity or speed. Let's talk about some types of glacial erosion. And one type of glacial erosion is called plucking and quarrying. So plucking means pulling something up, and quarrying means removing it and carrying it away. Kind of like a rock quarry, where you mine rocks and then you use them, you carry them away. So here's sort of a animation that represents that idea. This is a side view from a glacier, and we're going to animate it. So we have pieces that are getting pulled up, being plucked up from the bedrock and incorporated into the glacier and used in that glacier for erosion that happens elsewhere in the glacier. And all these materials are carried away. A second way that glaciers erode is through abrasion, just rock that's carried by the glacier coming in contact with bedrock. And you can see that here in this example of a very smooth surface. You see the glacier here retreating in the background, but the glacier only recently passed over this rock and helped to smooth it out. And we can see some examples of this idea of abrasion here in this glacial polish. That's me on the left many, many years ago in Alaska at Kenai Fjords. And you can see this rock hammer, that portion of the glacier right there that looks like it's wet really isn't. It's just really, really smooth bedrock that's been affected by glacial abrasion. We also have some terms that we use when the glaciers cut down into the bedrock. We refer to those places where grooves have been created. We call them striations or glacial grooves. And these photos are from glacial grooves on Kelly's Island Park in Ohio. And you can actually take a compass out, like a compass that points to the north, and you can see that these glacial grooves represent glacial ice that came from north and went directly south. So you can basically tell where you are on the island based on on the location of these grooves. Something else that glaciers do in this process of abrasion is they tend to remove material a little bit. They tend to, I guess you could say, smooth things out on what's called the Stoss side of the glacier. The Stoss side of the glacier represents the direction from which glacial ice was moving. So on the Stoss side, they sort of remove material, but it's sort of in a smoother way. And on the other side, as the glacier kind of climbs up over a little berm and comes back down the other side, then you see more destruction taking place on the lee side, away from the direction of movement. So on the lee side, you see things getting kind of torn up. And here we see on the example that I put on the right, the lee side of a glacier. So smoothing on the Stoss side, the uphill side, and on the downhill side, we see a lot more stuff that's pulled up through plucking. Here's an asymmetrical hill that sort of gives you an idea of glacial movement. You can sort of imagine that the glacier was coming from right to left and was passing down from higher elevations. And I'm sort of showing that as well in the upper diagram. So more smoothing over on this uphill side, and more tearing up and breaking up the rock and fracturing the rock over on this downhill side. A little bit about transportation by glaciers. I've said before in a previous video that glaciers are like conveyor belts, and I think that's a great way to think of them. They're constantly carrying material down slope. The movement in the glacier is the fastest up near the top. It's much slower down in the basal ice near the bedrock. But think of these glaciers as transporting things like conveyor belts. And anything carried by a glacier gets a generic name. We just call it glacial drift. So anything carried by glaciers. So here we see some trees that have sort of grown up over glacial drift. You know, if you look at the size of the particles carried by this glacier, they're all different sizes, from boulders down to stuff that's very fine, you know, finer than sand, maybe in silt or clay consistency. All right. Also want to mention some impacts of running water. So if you have glacial material that's materially carried by glacier that's later picked up and carried by running water, it takes on some unique characteristics. So we refer to material that's been sorted by running water as stratified drift. So this, you see this picture, imagine that a long time ago a glacier carried all this stuff, and then rivers came along later and picked up the lighter, the smaller stuff, transported that stuff down valley, leaving behind the bigger stuff. So anytime you find material like in the picture here on the left, where the particle sizes are similar in terms of size, it's likely that glacial drift was stratified by water to become stratified drift. And here's some unstratified material, and you can see the difference. In the unstratified material, the particles are different sizes. So in the stratified side, you know, you see them of a similar size and very consistent because they've been picked up and carried by running water. Something else that we just have sort of a general heading, glacial deposition. When we look at where glaciers leave material behind, we call this glacial deposition. So just like we'll talk a little bit later when we talk about coastal landform processes, how beaches are an example of a depositional landform. Now, one type of material that is involved in glacial deposition is glacial flour. That's the very smallest stuff that a glacier can carry, and it's ground. It's very, very finely ground material, the consistency of like baking flour. And it clogs up rivers and streams in Alaska. So you look at this view right here and you see some water flowing. It looks pretty gray because that water in suspension is carrying a lot of glacial flour. It's one reason why if you go and hike in some parts of Alaska and you take with these water filters that have a pump system, that sometimes they get clogged up pretty fast because of the glacial flour. And it's also a reason that some types of fish have difficulty in streams that are clogged with glacial flour. Glacial fluvial deposition just refers to any material that's carried and then left behind by running water that reworks glacial material. So here you see the glacier in the background in this picture, and there's a river sort of, or a stream at the toe of the glacier that picks up some of that glacial material and carries it down valley and then deposits that material. So this is definitely stratified drift. When we were talking about stratified drift a minute ago, these are the smaller particles that are carried by the running water. The bigger ones are left behind. When we talk about glacial fluvial deposition, we talk about stuff that's been carried and reworked by running water. We give it a special name. We call it glacial till. So this is till here. Again, it was ground up by the glacier and then it was reworked by running water and maybe carried to some other location. So we use the special word till. And then sometimes glaciers carry really big rocks and chunks, and this is right in front of the visitor center at Exit Glacier near Kenai Fjords. So this big rock was transported a long way by glacier and left behind. We call this a glacial erratic. If you look at the geology of this rock and you compare it to rock you would find anywhere else in this valley, it would most likely be different because the rock has been transported and carried by a glacier and then left behind. And here's, if you go to New York City, Central Park, you can find some examples of glacial erratics like this one. Kind of an impressive glacial erratic. You see some of it where she's standing there, that sort of smooth ground or ground that's been smoothed out by glaciers. Let's talk a little bit about the aftermath of continental ice sheets. We know that these ice sheets that covered the Earth during the Pleistocene developed in subpolar areas, remember around Hudson Bay in the case of the Laurentide ice sheet, and also mid-latitude areas, and then spread outward in all directions, including poleward. Glacial ice covered almost all pre-existing topography, just wiped out anything that was there. One example of we can see in terms of, and this is sort of a kind of a time-lapse thing that takes you through the Fraser glaciation that affected the area where Seattle is located. So if we kind of recycle this video a little bit here, you can see Seattle would be located here in this left image, sort of in the upper right-hand corner of that image. And the Fraser glaciation that lasted about 10,000 years covered the area that is now Seattle, Tacoma, where Mount Rainier National Park is in that portion, that part of Washington State, and also a portion of British Columbia, Victoria Island, and Canada. To give you an idea of how far south the Laurentide ice sheet, remember this is the ice sheet that's associated with the Pleistocene, the last glaciation, to show you how far south it came. This is sort of at its height. This is when the glacier, the glacial ice and the ice sheet, it made its farthest extent to the south, and this is about 18,000 years ago. Now, one of the things I want you to watch, I'm going to go through a series of slides here. Watch the area that I'm showing in gray right here. That's an area that was not covered by glacial ice during the Pleistocene and some of the other previous glacial periods. We call this place, that's shown right there in gray, the driftless area. So as the glaciers started to recede, or 14,000 years ago, you see some lakes are starting to form. These paleo lakes are starting to form with glacial meltwater. And there's the driftless area. We see the beginnings of Lake Michigan, a little bit of some other the other Great Lakes, and lakes just continue. There's that lake that was formed, that really big one that I talked about, Agassiz, that was formed with glacial meltwater. Here's 10,000 years ago, about 8,000 years ago, and finally we'll look at Lake Ontario. Of course, is one of the Great Lakes that was formed by, or I should say, as the glaciers receded. If you've ever been to the upstate part of New York, perhaps you visited the Finger Lakes region of New York, and you see these Finger Lakes are just these very elongated lakes. Here I show a couple of kind of close-up or more close-up views of the Finger Lakes region of New York. These represent where glaciers came down these valleys, these river valleys at one time, and over time receded and are, of course, are completely gone today. But those river valleys that exist today were formed by enormous valley glaciers. Just to show you the kind of the effect of the Laurentide ice sheet and Pleistocene glaciation, ice sheet glaciation, the zone of scouring shown here is an area where just everything was just removed by the moving stone ice. And then zone of maximum erosion, even quite a bit of erosion happened there. This area, zone of deposition, is where some of that stuff that was eroded through the scouring process and erosion process of glaciers or these continental ice sheets removing material. This is where it was deposited, the zone of deposition. So we find a lot of stuff. So we can thank the people in Canada for a lot of the soils and material that covers the northern part of, or sort of the northern central part of the U.S. today. Here's that driftless area that I was talking about. So I mentioned that this is an area that was not glaciated, and it's this area that sort of straddles Wisconsin, Minnesota, Iowa, and Illinois, and it has some bluffs that you just don't find in other places in this part of the country. Most of the land in these states is pretty flat, with a little bit of undulation, but not real tall mountains or bluffs, and this is one exception in the driftless area. And here's another view, the Wisconsin Dells, really pretty place to go in the driftless area. Again, an area that was not covered by Pleistocene glaciation, left behind. Okay, so deposition by ice sheets, the stuff that was left behind. I like this slide because it sort of, again, illustrates the extent, the maximum extent of the Laurentide ice sheet. And then in the slide at right, that's not the Laurentide ice sheet, but that sort of gives you a feel for what it might have looked like as the ice sheet was beginning to recede a little bit. And we can also see that here in the edge of Greenland's ice sheet. So we can sort of imagine what it might have looked like 10,000 years ago. Couple things that happened during this as the ice sheets began to retreat, or at least during the time when they were depositing material, they were leaving stuff behind. So these conveyor belts, these massive ice sheets as glacial conveyor belts left behind some features like the one you're looking at in this picture. And I added the Atlantic Ocean so you can get an idea of where you're looking at. So what does that look like to you? Maybe you can recognize it, and maybe you've got it. It's actually Long Island in New York. So that's Long Island. Long Island is a massive terminal moraine. And I'll show you a couple of others, and then we'll talk a little bit about terminal moraines. Another one that you might recognize is this peninsula. And the giveaway there is the thing that says Cape Cod Ice Lobe. So you're looking at the peninsula that's today, that's Cape Cod. And there's another one over a little bit to the west of it called Buzzards Bay Ice Lobe. So today we know Martha's Vineyard Island is there, and we have Boston would be the center top. That would be the location of Boston, Mass. And this is Cape Cod Bay that was formed by Pleistocene continental ice sheets, or that Laurentide ice sheet. We'll come back and look at terminal moraines a little bit later, but they basically represent the maximum extent of the glacial ice where the and where the conveyor belt was dumping material, and that's what created Long Island and Cape Cod, Cape Cod in Massachusetts. Another type of moraine that I want to talk about briefly is something called the recessional moraine. The recessional moraine is where, and this is sort of a side view here in this bottom panel, where a continental ice sheet begins to sort of stop for a while and dump material. So as it recedes, as it sort of disappears back up into higher elevations, it'll stop occasionally. It may advance a little bit, but it'll stop, dump material. And so you always only have one terminal moraine, and that represents the maximum extent of how far the continental ice sheet extended. But you might have a couple of different recessional moraines that are left there as the ice sheet sort of stops for a moment, or stop for a period of time, and dumps material. There might be a whole series of recessional moraines. We can sort of see that here in this animation. And here comes the continental ice sheet in this animation, and you can see it's just kind of obliterating everything. And the ice sheet will go to its maximum extent, and then it will dump that material. And this line here that's left behind is the terminal moraine. It advances again, maybe when the climate gets colder, and it leaves behind a recessional moraine. It advances again, but stops and recedes again, and it leaves behind another recessional moraine. So hopefully you can sort of see how that works. The ground moraine is just where the continental ice sheet, just the area underneath the continental ice sheet that was just all torn up by the continental ice sheet. So this is a ground moraine here, just underneath the ice sheet. And here we see, if you can visualize it, sort of imagine over on the left-hand side of the photograph is where the continental ice sheet was. And the ground moraine is just where the ground is all torn up, and there may be some material that was left behind by the glacier. Sort of ground up by the glacier. Here we see the terminal moraine, the maximum extent of that glacier, and the toe, where the toe of the glacier was, and where material was dumped by the conveyor belt. And then over on the right-hand side of the photograph, you see some unglaciated land. So that land was not glaciated at all. It looks nice and flat and even. Okay, one other thing to mention that's left behind by continental ice sheets are things called drumlins. A drumlin is a sort of a teardrop-shaped pile of debris that's sort of trapped underneath the continental ice sheet. And you can tell the direction of ice movement if you find one of these things on the ground. If you look at the teardrop shape, that kind of wider part would represent sort of the upslope area, if you will, of the moraine. The moraine has this sort of, like I say, it's almost like a teardrop shape. This is a side view and a top view of a drumlin. I'll show you some examples of drumlins here in just a minute, so you can see what they look like on the landscape. But again, imagine that these things just represent a bunch of debris that's at the bottom of the ice sheet that just sort of builds up. It gets all ground up and build up, and when the ice sheet disappears, you find these things on the landscape. Here's what they look like sort of underneath the ice sheet. So here we have this ice sheet, giant ice sheet, and then the drumlins with material and the material is all of all different sizes of particles. So big particles, small particles. These drumlins have not been reworked by running water. It's just what the glacier itself did. And here's what they look like if you go and see a few. Here's a drumlin in upstate New York, and you can see just from the shape that the snow and ice was coming from the upper right-hand corner, and it went from upper right-hand corner to lower left-hand corner of this view. So that you can sort of get some idea of which way the material came. Here's a cutaway of the drumlin, so you can see the kinds of materials that you find in the drumlins. They're all mixed together, small stuff, big stuff, and some unusual drumlins. There are some that have been cultivated, where they're growing stuff on drumlins and near Eagle, Wisconsin. And this view is from a drumlin in Germany. And when I look at this slide, it's obvious that the people that lived in this area decided that they wanted to keep the flat land, the nice flat land for farming, and they went ahead and built their homes on the drumlin. So the actual town is built on top of the drumlin, and the agriculture happens elsewhere. I wanted to also talk about a few glaciofluvial features. So these features are created by water, running water typically, and And so one of those is called kettle, and this is where a giant chunk of ice is left behind by the ice sheet. So imagine a chunk of ice left behind, like this lower diagram that I've created right here. So buried chunk of ice sheet retreats, chunk of ice melts and becomes a lake. And we call these lakes kettle lakes. So all of these lakes shown in this this view, this is in Siberia, in Russia, are kettle lakes. They represent places where these chunks of ice were left behind that created the depressions, and the chunks of ice melted pretty quickly and created lakes. And some of these are pretty beautiful. Here's a kettle lake in upstate New York. Actually has a obviously a waterfall, a river running into it and also flowing out of it. Kettle lakes in Siberia, I mean, they're everywhere. If you have heard this term and you see it on the Minnesota license plate, car license plate, land of 10,000 lakes, have you heard that term? That's on the license plate, or at least it was on one version of the license plate a few years ago. That comes from the idea that all these lakes that you find in places like Minnesota, Wisconsin, elsewhere in the northern Midwest were created by chunks of ice that were left behind. They're natural basins for lakes. Okay, a couple of other things. Came is a big pile of debris that has been reworked by running water at the bottom of an ice sheet, and the ice sheet recedes. It leaves behind the stuff that has, in fact, been reworked by running water, and it's just a big pile of debris that's carried by water flowing at the bottom of an ice sheet below where you could see if you were there. So a kettle is sorted material. The pieces are of similar sizes. It's considered stratified drift. So here's kind of my time-lapse view. That little panel in the lower left-hand side, you see the came there at the bottom of the ice sheet. The ice sheet retreats, and it leaves the came behind, just like you see in that photo at the top. Here's another example of a came. So again, if you were to take a shovel out and dig into one of these, you'd find that the materials are all pretty much the same size because it's stratified drift. It's stuff that was ground up by the glacier, carried underneath the glacier by running water, all piled up and kind of left in a big pile at the bottom of the glacier. So here's they've actually used this came for building materials. So you can see somebody's been in here with an earth mover and has removed some of this sandy, gravelly stuff for some purpose. Also, at the bottom of ice sheets, sometimes you find these rivers that will push material out of the way, and that forms what's called an esker. So an esker represents where water was running as a river underneath a continental ice sheet, and material carried by that under ice river piled up on one side or both sides of that under ice river, and we call these eskers. And the esker in the photograph here with all the green there, those are trees that have grown up on top of the esker. So the continental ice sheet has long since disappeared, and the esker is left behind. So they form these kind of snaking things that are kind of interesting. Here's another example of an esker and some students looking at an esker. Again, similar particle size, stratified drift, smaller particles carried away and piled up. So here's a kind of a longer esker in the Northwest Territories of Canada. Again, so you can visualize what these eskers might look like. Here's a subglacial tunnel carrying with water traveling in it. So there may be material that once this snow and ice is gone, once this glacial ice is gone, you might find an esker underneath this thing where the water was sort of pushing sediment out of the way. Again, I've used this term already, so I'll just have it on this slide, but stratified drift, just a reminder, is sorted material where smaller materials are carried away by running water, leaving behind the bigger ones. Poorly sorted materials are not considered stratified, but over here where the red box is around that, similar sized particles stratified. So if you're ever looking at glacial material, you can almost always tell when water has played a role in reworking things. An outwash plain is just a big area of, at the toe of a glacier where you find a lot of stratified material, a lot of melting going on, and water that's there, the meltwaters. So all this stuff over here, this is a big stratified, or big area of stratified drift, this big outwash plain here at the toe of this glacier. To sum it all up, so you can see here's some of these features, just so you can sort of visualize them once again. The esker, the drumlin, the outwash plain, the terminal moraine, the came, the ground moraine, so you can sort of see how they all are found associated with the retreating continental ice sheet. Last topic, very briefly, I just want to say a few things about glaciation in mountain areas. Once again, this concept, this idea that glaciers don't create landscapes, they modify existing ones. So what glaciers do is they come along and they take, when they fill, for example, and ice and snow builds up in these valleys that were never glaciated before, they convert V-shaped valleys into U-shaped valleys. And let me sort of show you how that happens. A V-shaped valley is dominated typically by a river where the erosion is focused just in one point. Here in the center, you see where I have this arrow in that little blue. That is representing the profile of this river below, where most of the erosion is happening. You might have some mass wasting on the side of the hills, but the erosion where the river cuts down is really happening in one place. So imagine if you fill this valley, if you fill it with glacial ice. So here's a valley that's been filled with glacial ice, valley glacier. Now the force is not just in one place, it's all the way along the sides of the valley. Can you see that? It's all the way along the sides of the valley. So it's these glaciers are very effective in modifying landscapes, and they're in removing material. So super efficient way to remove material. When the glacier's gone, here's what you see: a valley like this one. You might see a return of a stream in the bottom of the valley, but it's now this V-shaped valley. Previous V-shaped valley has been converted over time by a valley glacier into a U-shaped valley. And you can kind of see that here. This little animation kind of does that. We fill the valleys full of glacial ice, and then we make it go away, and you can sort of see how that might happen. The photograph on the left is a U-shaped valley. Some really famous U-shaped valleys you can see: New Zealand, South Island. This is in Fiordland National Park. Nice U-shaped valley there, shown sort of in the center, really on both sides of that center part of the photograph. You can see the U-shaped valley. One of the most famous U-shaped valleys is this one, Yosemite Valley in California, Yosemite National Park. Try to imagine this whole valley filled with the main valley glacier, and this glacier was so big at one time that it carved and removed one half of what used to be a full dome. So if you look in the upper right-hand corner of this photograph, you see Half Dome, which is a really famous thing that climbers, there are a lot of climbers want to get to the top of this thing. They climb the face of Half Dome, the steep face of Half Dome. Well, this used to be a full dome because this, there was a lot of rock that was removed by this main valley glacier. Okay, a couple of features in mountain areas, some glacial features. The terminal moraine is similar to the terminal moraine. We talked about it related to continental ice sheet glaciation. So here's our terminal moraine on this bottom left corner view. We have the glacier and the terminal moraine. Right there at the toe of the glacier is the conveyor belt is dumping material. That's what the terminal moraine is. And when the glacier recedes and begins to disappear, you see the terminal moraine is left behind. Mountain glaciation has a couple of unique types of moraines that I wanted to mention. I alluded to this briefly in an earlier video, but this is a medial moraine. This is a main valley glacier here. With these black stripes, and the black stripes represent the boundary between glacial ice contributed by cirques that are way up valley. So you have some up valley cirques way up in the higher elevations, and there's snow and ice that comes together outside of where you can see in this photograph, kind of like rivers that come together, that you have the sort of the confluence of two rivers. You have the confluence of two of snow and ice coming from two different cirques. Those cirques located near mountaintops, and where that snow and ice comes together, between the snow and ice that's contributed by each cirque, you see some debris that's pushed out of the way, and that is the medial moraine, those dark lines. So every one of these dark lines in the lower image represents the boundary line between snow and ice that has been collecting and started in a moraine that was way up valley. So if you count the number of medial moraines, and you get to a big number, you can certainly imagine how many smaller glaciers contributed to this main valley glacier. And here's another example. You can just count a lot of lines there. You can count the really big ones, and there's even smaller ones that are a little bit harder to see. One more view of medial moraines. That's debris that's pushed out of the way. That's rock material that's pushed out of the way. And another view of a medial moraine. Here's a medial moraine kind of after the snow and ice are gone. You can sort of see what they look like without the glacier there. So there's a glacier over here to the right. There's a bigger one over here to the left, and that's the medial moraine. That's that debris that was trapped as the glacier continued to move down valley. Or one glacier, one giant valley glacier that had a whole lot of smaller glaciers contributing to it. Lateral moraines are places where a main valley glacier has pushed debris off to the sides, like the medial moraine, but just a single, just where you find it sort of on the side of the valley. These are lateral moraines. Here's a crazy person in the photo, but a lateral moraine over on both the left and the right-hand side of this photograph. Here's another example of a lateral moraine, stuff that's pushed off to the side by this main valley glacier. So you find lateral moraines just on the sides of main valley glaciers. Here's another one, lateral moraine. You can see that all that debris that's now uncovered. You know, the glacial ice is mostly receded, and you can see that a little bit better in that photo. So when glaciers come across and affect the tops of mountains, they oftentimes create what are called arêtes, these really steep ridges. And I'll show you what a col is in just a second, but arêtes and cols are associated with the tops of mountains. Here's an arête right here. Pretty impressive one. This is where, you know, if you're climbing some taller mountains, you may have to sort of walk along. You can actually see some climbers in the center of the photo. You need to sort of walk along these arêtes, and it'd be pretty challenging. But an arête represents where there's a glacier on each side of this hill. So you actually see a glacier there with glacial ice, and that's removing rock all the time. There's also probably a glacier on the other side where we can't see it that's removing rock, and that process of rock being removed on either side of that produces the arête. A smaller arête is oftentimes given the name minaret. So if you ever hear that term minaret, it's kind of a small arête. And then a col is just a sharp edge pass or saddle between arêtes. So the col is the low point between two, and these are two minarets, two smaller arêtes. How about a horn? A horn is a mountain that has been affected by by glacial ice on several sides. And when you look at this picture of this horn, try to imagine this thing was rounded at an earlier time, and that the glacial ice on each of the faces removed the rock material and made this thing very sharp. And you know, here's another example of a horn, the Matterhorn in Disneyland. I think Disney World has a Matterhorn as well. I haven't seen the one at Disney World, but I've certainly seen the one at Disneyland that's made out of fiberglass, so sort of a fake horn, but you get the idea. Here's the formation of a horn, how you might imagine a horn forming. So pre-glacial, before the glacial ice came, you had a nice rounded mountain, and the glacial ice came along and started removing material, this erosive effectiveness of the glacial ice on each face, on each side of the mountain, and you convert something that was a nice rounded mountain into something that's pretty dramatic. So we have the formation of a horn, and here's the horn right here that we formed in that last image. That was sort of a rapid time-lapse image. A couple of other features. We'll finish out Tarn Lake. Tarn Lake is a lake that is formed in the bottom of a cirque, and they oftentimes are really beautiful. High altitude lakes. I know the ones in the Sierra Nevada mountains in California, they don't naturally have fish in them, and the U.S. Fish and Wildlife Service actually stocks them with fish, and sometimes they use helicopters and they dump the fish into these lakes, so you have great trout fishing in these lakes. But here's one example of a Lonesome Lake as an example of a Tarn Lake forming in the bottom of a cirque, naturally carved out basin. I sort of show in this lower image right here how that could happen. So you have the cirque with snow in it. Snow melts, disappears, and it creates a natural basin for a Tarn Lake. Here's a couple of Tarn Lakes. Sometimes you have a whole series of Tarn Lakes that form where you had a series of cirques as you went down mountain, and when the snow and ice and the glacier's gone, you have what are called Paternoster Lakes. So a series of this Tarn Lake drains into this one. This Tarn Lake in the middle drains into the one at the lower part, and this term has the meaning of our Father in German, Paternoster Lakes. So, finally, we've got hanging valleys are really pretty interesting. Hanging valley is where a smaller tributary glacier or perhaps unglaciated valley comes in contact with a main valley glacier. So when you look at this image, this photograph, try to imagine a main valley glacier, a massive glacier filling this entire valley. And this U-shaped valley here would represent a smaller glacier joining up with that main valley glacier. So the smaller glacier, the erosive effectiveness is not as great because there's not as much snow and it may not be moving as quickly. When the glaciers are gone, it leaves this hanging valley because this smaller tributary glacier just wasn't cutting down as quickly as the main valley glacier. So that's what a hanging valley is. You can also have a V-shaped valley, an unglaciated valley that you find. that comes in contact or joins up with a main valley glacier. And you see some really beautiful waterfalls in Yosemite National Park. There's Bridal Veil Falls, just an absolutely gorgeous place where a hanging valley exists in Yosemite Valley, something you really want to see. And here's kind of how that's happening one more time. Here's the main valley glacier, and you see here's the tributary glacier, and then the hanging valley, and then we contemporary, we have a river flowing through this tributary glacier that forms this wonderful waterfall. And one more example, just so you can see sort of real life. This particular main valley glacier is now filled, now created a fjord, but it indeed is the same as the other example.